Hello, 12 Math B, and thank you for joining me. If you're here, then that's good. You've strapped yourself in for 20 minutes. I don't know how long this will take, but let's say 20 minutes. And you're willing to put up with my voice for that long, and hopefully this will help you. So I'm going to go through now and talk to you through the entire integration topic that we've done. I understand that obviously this is recorded in 2017, so with the musical this year, it's been a little bit tricky for quite a few of you to keep up with your work, and it became pretty apparent last week that maybe some of you needed this extra support. So I'm going to put this together now. Hopefully it will help. It will start from scratch with integration, work the whole way through with examples, and then you can ask me more questions, obviously, moving forward into the future. So here we go. Let's start with the basic integration laws. So I'm just going to write these down as the general integration rules. Now, you know quite a number of functions now, and you've worked with quite a number of functions. So these are the rules that you'll need to know and be aware of, and they're all fairly simple. So first of all, for polynomials, if we integrate ax to the power of n dx, then this becomes ax to the power of n plus 1 divided by n plus 1 plus c. So it's really important here you recognise with polynomials, we raise the power by 1 and we divide by the new power. And that's the opposite to when we differentiated and we multiplied by the old power and we brought the power down by 1. The second one is that the integral of cos x dx is equal to sin x plus c. And matching this is the integral of sin x dx is equal to negative cos x plus c. So sine goes to cos when you differentiate, which means that cos goes to sine when you integrate. And cos goes to negative sine when you differentiate, so that means that sine goes to negative cos when you integrate. And you get that matching. And there are two more for you. The next one is probably the easiest of the lot. The integral of e to the x dx is equal to e to the x plus c. And then the integral of 1 over x dx is equal to the natural log of x. ln, you recall, is the same as log base e. So there are our 5 integration rules. They form the basis of what you need to know and be able to do. Now, obviously, in differentiation, you've spent a lot of time working within a range of problems, quite complex problems with the quotient rule, the chain rule, and the product rule. And there's a real depth to what you need to be able to do. But with integration, it really is just skimming on the surface in the Math B curriculum. So you will need to know how to integrate these 5 functions, and you'll need to be able to integrate fairly simple versions of these 5 functions. And I'm going to talk to you about some of those now. So let's move on to our second section. What about if there's a linear function within any of these? So if they include a linear function, and this just makes a slight difference to just that x. X is obviously a linear function by itself, but it's a very standard form, just equals x. We're going to change that x now, and instead we're going to insert 3x plus 7 into some of our questions to see how they look then. So let's imagine we're integrating 3x plus 7 to the power of 7 dx. So in this case, we follow that polynomial rule, and we write this down as 3x plus 7 to the power of 8, and we divide by 8. But we have this other little issue, and it's this 3 here. If we derived d dx 3x plus 7, that will give us 3. So if we were deriving this function using the chain rule, we would get an additional factor of 3. And that means that when we integrate, we need to remove that additional factor of 3 by dividing by 3. So it takes away that additional factor of 3. And I get a plus c. So this is now equal to 3x plus 7 to the power of 8 over 24 plus c. Now let's say we had this question, b. The integral of 1 over 3x plus 7 dx is equal to this. Now we've got that 1 over 3x plus 7, and we can write that down as log of 3x plus 7. But again, in this case, we have to be very careful because it's not just log of x, there's a 3x plus 7. So if we derived that function, the log would make it 1 over 3x plus 7, giving us the integrand that we're working with, but we would have to use the chain rule, and we would have to also derive the inside function, which would give us that extra factor of 3 again. So in this case, we need to also divide by 3 and add c. So we get natural log, or I might write it down as a third, natural log 3x, and I should be using absolute value signs for these as well. You don't need to worry too much about y, but with logs we use absolute value signs as you can't take a log of a negative number. So I'm just going to change and update this, plus c. I won't be able to edit that little mistake out. And then question C, a third example. Let's say we were dealing with the integral of sine 3x plus 7 dx. And I hope now that you're starting to see the pattern. So the pattern here is that we write this down using our standard integrals as cos of 3x plus 7, but we have to divide it by 3 again, plus c. And so it becomes 1/3 cos 3x plus 7 plus c. And so that's our rule. Now I'm just going to shoot back up to our standard rules here, and I'm going to add a second set of rules so you can see them. If we have the integral of a, so we'll leave that a there, and we have px plus q, so a linear term now to the power of n dx, then this will become px plus q to the power of n plus 1 over n plus 1, which is our standard what we have to do, but also divided by a factor of p plus c. So we've got that additional little, we have to divide by p as well. Everything else is the same, but we also have to divide by p. Cos px plus q to the dx equals sine px plus q over p. And the rest follow. So I'm going to do this in silence and then fast forward it on the video. Wow, how fast is my writing? Okay, so they are the standard integrals where you have a linear function, and that's really about as far as you need to go. We do have some more challenging questions that do involve nonlinear functions outside, but for Math B, you only need to be able to do some simple observations. So let's have a look at integration by observation. So for integration by observation, it's just a case of having a problem where you need to be able to see two key factors to the question. And let me just show you an example. Let's say we had e to the power of f of x. But I'm going to write this down for my example as e to the power of x squared. So you can see now it's not a linear function inside of our big function. Our big function is e. And let's say we derived that function, d dx of e to the power of x squared is equal to e to the power of x squared again. That's how our function ex works. But we have to multiply by the derivative of the inside function. So this is the chain rule. And so that equals e to the power of x squared times 2x, or 2x e to the power of x squared. Now at this stage, it'll be handy for you to recognize that because we derived to get from here to here, then we just need to, if we integrate the second function, 2x e to the x squared dx, then this will be equal to just e to the x squared plus c, because deriving is the opposite to integrating, so therefore integration would take us back. But here's the more important part. This and this term are related. The 2x is our f dash of x, and the x squared is our f of x. So now we're dealing with a situation where inside the exponential, inside that big overarching function, e to the x squared, we have a function. And on the outside, it's just a multiply, we have the derivative of that inside function. And if we have those two key components, then we can integrate this by observation. We can recognize that when we integrate this, we end up with just our original function here, and this f dash of x here will get sucked up back into that chain rule reverse operation there. So let me give you some examples. Let's say we were dealing with something quite similar. I'm going to stick with the x squared for now. Let's say we were integrating 2x cos of x squared dx. And this would be a case of recognizing that this is our f dash of x and this is our f of x. And so therefore, if I write this down as sine of x squared plus c, that would be our integral, because the cos x squared would go to the sine x squared, and that 2x will get sucked up in the derivative of that x squared. But you know, it might be better, it might be easier for you to write it down like this and consider it like this. And this step is a little bit mathematically incorrect, but I'm going to show it to you anyway, and we've talked about it in class. So let's imagine instead you recognized that this still has a 2x, and just like in previous questions, we have to derive by the inside, divide by the derivative of the inside function. So we divide by d dx of x squared. And so this will give us 2x sine x squared over 2x, and they will cancel, leaving us sine x squared plus c, and I should put my plus c there. So it's a really nice way of doing it, recognizing that if we were to derive this function, we would end up with a chain rule situation, and we would have to multiply by the derivative of x squared. So when we're integrating, we have to divide by the derivative of x squared to even out the ledger. And by doing that, we remove that 2x. But this will only work if this out the front, this function out the front is f dash of x. If that was 2x cubed, this would not work and we would not get the right answer. So you have to be very careful to understand this method only works when you've got f dash of x as the multiplier. So let's have a look at some other examples. The integral of sine x e to the cos x dx. So this is an example again where we don't have a polynomial as our f of x this time. In this case, I can see that cos x is my f of x. It's my inside function. It's inside the big thing, which is the e to the power of cos x, the big chain rule thing. And sine x is my f dash of x. And so I can write my answer down as sine x e to the cos x, because remember e to the cos x just goes to e to the cos x, but I have to divide this by the derivative of the inside function, which is cos x. And again, this will only work if that derivative of the inside function will match that multiplier, which is sine x. And so I get sine x e to the cos x divided by negative sine x, because the derivative of cos x is negative sine x. And that, of course, cancels there, and I get negative e to the cos x. And, of course, because I've integrated, I've got plus c in each case. So there's my solution. That's a really procedural way that you can set it out, but you will get the wrong answer if you haven't identified the f of x, f dash of x correctly, or that it exists. One last example for you. Let's integrate 2x squared over 5x cubed plus 1. And I've deliberately done this question because the constant that we get, the remaining constant's quite tricky. So you could do this by observation, you could do it quite quickly, but it's a bit of a problem. That constant's a bit of a problem. So let's have a look at this and identify some things first of all. This is my f of x, and this is my f dash of x. And this is a pretty standard type of question. The result is that my f of x is part of a bigger picture 1 over 5x cubed plus 1, and that of course goes to log of 5x cubed plus 1 when I integrate that. But we still have this 2x squared multiplier there, and of course we have to divide by the derivative of 5x cubed plus 1. And so now I follow through with this. I get 2x squared log 5x cubed plus 1 divided by, and the derivative there is 15x squared. And that's good because the x squareds will cancel, and they should do, and if they don't, then you are doing the question incorrectly. And I get 2/15 of log 5x cubed plus 1 plus c, and plus c. Don't forget your plus c's. They will be work marks. So that's integration by observation. It's about recognizing that you've got an f of x and an f dash of x within the function. And so we've talked now about the standard integrals, the standard integration laws. We've talked about integration where you have a linear function inside. And now we've talked about integration where we have an f of x and an f dash of x combination. And that's really all you need to know how to do. I'm going to show you one particular context now, which we talked about late last week, to do with growth and decay. And there's a whole bunch of different subcontexts to this, but growth and decay is the big picture. So population growth or anything like that. And I'm going to talk to you about it in terms of Newton's law of cooling. So growth and decay is an exponential function. It's where a population is growing, and as the population grows, it can grow quicker because there's more population to help that growth. Or decay, it's where a radioactive element is decaying over time, but it only decays depending on how much mass there is. So as it gets smaller, it will decay slower. Or in this case, Newton's law of cooling. So imagine you have, and you may have done this kind of thing in science before, imagine you have a cup of warm water. Now this cup of warm water at the moment is, you've just boiled it, let's say, so it's not quite 100 degrees, but let's say it's 90 degrees. The difference between it and its surroundings in terms of temperature is quite large. So it is letting off heat very quickly because it's moving towards the temperature of its surroundings. But if you have a cup of warm water that's 90 degrees and your surroundings are 20 degrees, it's going to cool down quite quickly. But if you have a cup of water that is 21 degrees and the surroundings are 20 degrees, it will continue to move towards the temperature of the surroundings, but it won't be moving so quickly. So graphically, that's going to look like this. The water will start at 90 degrees here, and it will move towards that temperature of its surroundings, which often we'd call room temperature. And so this will be our room temperature, and this will be our starting point, 90 degrees Celsius. And you can see that that's an exponential function, but in this particular exponential function, we've got a special property, which I'm going to talk to you about now. So let's have a look at this. Newton's law of cooling states that the rate at which the body cools is proportional to the difference between the temperature and its immediate surroundings. So that being this difference here. It's proportional to that. And as that difference gets smaller, it will cool slower. Think about that logically for a minute. It makes sense. So that's the first thing. Now, using Newton's law of cooling, we can clearly identify a relationship. It's saying, let's define some variables first for this particular question. So it's saying an iron bar is placed in a room that has temperature, blah, blah, blah. So let's say that T is the temperature of the bar. Actually, I don't have to define them because it's written here. T be the temperature of the bar, and little t is the time in minutes. So the rate of change of temperature is dt dt. And the claim there is that rate of change of temperature is decreasing proportionately to the difference between the original temperature and room temperature, 20 degrees. And that makes sense. It's decreasing at that original temperature and room temperature. So I'm going to do some work now, and it's going to lead down to this function. It's going to lead down to that temperature is equal to the initial temperature times E to some constant times time. And K will be less than 0. And I know K will be less than 0 because this is a decay problem. So the temperature is decaying over time. If it was a population growth problem, then K would be greater than 0. But in this case, K is less than 0. So I've got that situation. And I'm going to work through this, but I'm actually going to do it for a simpler question. And then I'll do it for this one. I'm going to do it for a really simple problem first of all. So let's just leave this one for a second. I'll put a little asterisk there. And let's just move to the side over here and talk about a really simple example where we say, what happens if the temperature or the rate of change of a population, P being a population, is proportionate to just P? And again, think about this logically. If you have a population of something, let's say bacteria, then that population will grow based on, at the speed that it grows will be based on the number of bacteria present, because they are obviously repopulating themselves. So the more bacteria, the more they can produce. So this is true. And that means that dp to t, because this is the rate of change of the population as per time, is equal to some constant times p. That's what this proportionate sign means. So if dp to t is proportional to p, then dp to t is equal to a constant times p. And now I can go through this exact procedure that you should know and be aware of to integrate this function. So I'm going to split my differential. This is my differential here, my rate. I'm going to split that up into dp equals kp to t. And I'm going to, that's all good and well, I'm going to recognize that, but I can't integrate p with respect to t. So I'm going to bring the p across and write it down as 1 over p to p is equal to some constant to t. And now I'm going to actually integrate both sides. So I'll integrate there and I'll integrate there. I can do anything I want to both sides of an equation as long as I'm consistent. And this obviously means that I now have log p plus some constant is equal to kt plus some constant. Now, because I've got two constants, I'll write them down as C1 and C2. And now I'm going to simplify this and write this down as log P is equal to KT plus C2 minus C1. And notice that C2 minus C1 is just a constant. So it's 7 minus 3 or 10 minus 12 or pi minus E, whatever constant it is. But it is just a constant, it's just a number. So I'm going to write this down as another constant now and very, very arbitrarily choose B as my constant name, just for lack of anything else. So I've got little b as my constant name now, which means that log P is equal to KT plus B. Now I'm going to rearrange this. Remember that if you have, well, let's go back to our basic logs from term 3, 11, x to the, basic logs were a to the power of x equals y leads you to this logarithmic function. Log base a of y is equal to x. So I'm going to use that as a rearrangement here and recognize that obviously ln is log base e. And so I get P is equal to e to the kt plus b using that rearrangement. And now that I've used that rearrangement, I'm going to split this up, e to the kt times e to the b. That's a reverse engineering of one of our basic index laws, a to the m times a to the n equals a to the m plus n. And I've just reverse engineered that. And I'm going to now recognize that e to the b is just some constant. E is about 2.718 and b is something. We stated it was a constant up here. So I'm going to let that be a. And this will become a e to the kt, and obviously that's our population. So there's our population. If population growth is exponential, that's why it's exponential, because the rate of change is increasing proportionately to the population at the time. So there's a standard one. And I'm just going to, I'll put this on the screen now. I'll zoom in a little bit. And it's on the OneNote. I'll put a big box around it. Here are the list of things that have happened as we've gone. But you should know that. that run down there you should be well aware of, and you need to be well aware of. So I'm going to leave that there. You should pause the video now and write it down if you need to. Okay, just scooting back across then, let's do the same thing for this question. So we get this. dt, so zoom in a little bit here, is equal to k times t minus 20. And so therefore I can rearrange that to be dt equals k t minus 20 to little t. And I can do that little logarithmic rearrangement, so I get 1 over t minus 20 dt is equal to k dt. And I integrate both sides, and that gives me log of t minus 20 is equal to kt plus some constant. I've just combined the constants all in one go on one side, and on the side that I want it to be on. And so this obviously means that t minus 20 is equal to e to the kt plus c. And so t minus 20 is equal to e to the kt times e to the c. And t is equal to a e to the kt plus 20. So there we go. I've broken it down. I've let e to the c equal a, so I get that standard normalized exponential function there, and I've added 20 to both sides as well. This is a different, but it's only slightly different, and it gives us that 20. And so there's my function. Now that I've got this function, I can see it's going to match this. So this is an exponential function where k is negative, giving me growth. It will match this, but it has an asymptote at 20 instead of 0, and that's because of this plus 20. Function tells us that if we add 20, it shifts the whole function up, so the asymptote has moved up, and that's transformations. And so the question has stated that the iron bar has a temperature of 80 degrees Celsius initially and 70 degrees Celsius 5 minutes in. So I've got two pieces of information. At t equals 0, capital T equals 80. And at t equals 5, capital T equals 70. You should always have two pieces of information. The initial might sometimes be hidden, so just be aware of that. So now I change my capital T. Actually, you use 0.1, and because it's initial, it's quite easy. I'm going to substitute that in. And I get 80 is equal to a e to the k times 0 plus 20. And that means that 60 is equal to a times 1. E to the 0 is 1. So a is equal to 60. And that gives me capital T equals 60. E to the kt plus 20. And that 60 represents the difference between the initial temperature and room temperature. So that makes sense. That's our initial difference. In this case, we started at 80 and we went down to 20. That's a difference of 60. So we've got that function, and we also know that at little t equals 5, capital T is equal to 70. So I substitute that in. 70 is equal to 60 e to the 5k plus 20, and that gives me 50 is equal to, sorry, I've written 70 there, 60 e to the 5k, and so that gives me e to the 5k is equal to 50 over 60. Rearranging that in terms of a log again, I get 5k is equal to the natural log of 5 over 6. 50 over 60 is 5 over 6. And k is equal to the natural log of 5/6 over 5. And now I'm going to calculate that value. K equals negative 0.03646431136 on my calculator, and I'm going to say that that's equal to approximately negative 0.0365. Now, I can round and put this in, and obviously I need to. I don't be writing that number every time, but if you can, hold that value in your calculator as you do these questions. And so my function now is t is equal to 60 e to the negative 0.0365 little t plus 20. And notice my k value is negative, which is what we expected. Now I'll shoot back up to the question just to see what I actually have to answer. I've done this is all the groundwork. I've not even started answering the question yet. I've just built the model. Algebraically determine the time it takes for the bar to cool to 40 degrees Celsius. Validate this answer in your graphics calculator. State any assumptions. So I'm going to algebraically determine it. I'll just write this down as question A so you can see the split. I want to know the time it takes for T to equal temperature to equal 40. So I'm going to write down 40 is equal to 60 e to the negative 0.0365 T plus 20. And so I get 20 is equal to 60 e to the negative 0.0365 T. I now divide by 60. I subtracted 20 earlier, and I get, that ends up being 1/3 simplified, equals e to the negative 0.0365 T. I take a log of both sides, or I rearrange using log form, and I get negative 0.0365 T is equal to the natural log of 1/3, and T is equal to the natural log of 1/3 divided by negative 0.0365, or that value I've got in my calculator. So now I'm just going to put this in my calculator, and I get an answer that is 30.1284, and I'll leave it to 4 decimal places. So the question was, algebraically determine time takes bar Q, blah, 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 blah. Validate in my graphics calculator, but I just want to check it's in minutes. That's my unit, so I'll write this down, 30 minutes. Now my quick validation in my head is, does this make sense? 5 minutes it went from 80 to 70, 30 minutes from 80 to 40, it makes sense. I'm happy with that answer. And just thinking about it contextually, the fact I have a cup of coffee right next to me going cold, and I've been talking to you for about 30 minutes, it gives me a pretty good indication that that's true. So I'm happy with that. I would obviously now go and get on my graphics calculator, which I'm not going to show you now because you know how to do that. And I would sketch a function that looks something like this. And there would be my function with an asymptote at 20. And I would then substitute in t equals 40. I'd look for that t equals 40 there, and I'd check that when I map this down, it comes out at about 30 minutes. And that would be my graphic calculator validation. And assumptions that I need to state are things such as, there's a lot of contextual assumptions here. So room temperature doesn't change or vary and come back to the start. I don't have anything added or taken away from the cup, particularly in context of a cup of coffee, if there's milk added or something like that. So there's heaps of things you can talk about there in terms of assumptions. So that's it. That's really everything you need to know about integration. I really hope this has helped. You're welcome, of course, to come along and see me at any point and ask for any extra additional help. But otherwise, that's the topic. Make sure you're on top of it. Practice and consolidate. From here, from this moment forward, start on the first simple problems and consolidate your way through to the harder problems. Don't go away now and try and do a Newton's law of cooling problem if you're not sure about the previous work.